Good morning, everyone. It's a great pleasure for me to be here virtually with you today, and I would thank you a lot, the organizers, for inviting me to attending this exciting event. Before I begin with my presentation, I'd like to briefly introduce myself. I'm Angelo Massafra, and I am a PhD student at the Department of Architecture of the University of Bologna in Italy. Today I'm going to talk about a piece of my PhD research which is entitled Topology-oriented digital twins for the performance-based management of the built heritage. So let's start with the research background, and let's do it by considering some numbers. You may be aware of the impacts of the building industry and above all of the built environment on the world in terms of energy use, global carbon emissions, solid waste generation, but also material resource consumption and freshwater use. The key point to understand for this research is that, as you imagine, all these impacts occur during the whole life cycle of buildings and, above all, during the operation and maintenance phase. This means that we need not only new high-performance buildings, but also more sustainable building management practices. So, on one hand, building managers should consider a very complex framework to efficiently locate the technical and economic resources during the operation of buildings every day. On the other hand, they should consider the performance of buildings while satisfying the occupants' needs in terms of internal comfort, but also in terms of functional requirement of spaces. According to this scenario, new approaches are emerging in digital management, such as the occupant-based building management, in terms of safety, operation, and maintenance. So we need new digital tools to support decision making in order to supporting the management daily activities and giving also a reliable estimation of costs and impacts of the different action measures in building management. For example, about new planning of occupancy levels, new uses of buildings or of buildings areas, renovation interventions, and so on. My research specifically focuses on the operation pillar of building management, focusing also on university buildings. As we can see in this slide, the effects of building operation can be, in my opinion, divided in three main areas that are use, consumption, and impact. So space use, facilities needs in order to allow the functional requirements of these spaces, energy consumption, resource consumption, but also costs for administrators, environmental issues, and the well-being of occupants. If we need to allow the performance-based management of the built heritage, building operation aspects should consider all these 7 sub-areas in a quantitative form. So we need to identify some key performance indicators for each of these areas that could be related to the management action of building owners. To this end, I tried to set up a sort of performance-based management models for buildings that consider 7 main steps and that could support building managers during their operation. As we can see, we have in the first step the establishment of performance goal to reach for administrators. Then we have to establish some key performance indicator for measures this performance. Then we have to measure, so collect data about this performance, benchmark this data, and doing a sort of analysis of this data, predicting new targets in order to allow a future better performance of buildings, and finally predicting future performance according to the collected data and acting, so change management and acting with corrective actions, and then repeat all in this loop in order to evaluate the performance of the actions that we performed. So now I want to move to the approach. As you can imagine also by the title of the presentation, the need of dynamic data from the building and of real data about the buildings led me to think about the idea of implementing a sort of digital twin system for helping building managers in assessing the performance of building operation during their daily activities. As you know, a digital twin can be represented as a sort of information environment that abstracts structures, processes, and visualizes data about a real object, a real process, environment, or system. So a thing that exists in the real world. In our sector, in the IC sector, a digital twin can allow for describing, inspecting, monitoring, managing a built asset during its life cycle by using different kind of data that could be static data from BIM models, from GIS models, but also dynamic and real-time data from sensors or IoT devices that can be processed with intelligent algorithms, machine learning algorithms, and so on. As you can see in this framework, my digital twin is composed of 5 main entities that are the physical entity, that is the building as it exists in the real world, the virtual entity, that is the digital twin of the building. Then we have the digital twin data, that is a sort of centralized data environment that fuse and integrate all the data about the building. Then we have services that are very important because they allow building managers to interact with the digital twin data. And finally, we have connection between these 4 elements. In summary, the main goal of the research is to create a digital twin platform prototype that could support building management operators in evaluating the performance of building operation during their daily use in a dynamic and holistic way by integrating different kind of data that could come from BIM models, building performance simulation, sensors, and so on. The case study is one or two buildings in my university that are the School of Engineering and Institute of Mathematics that you can see at the right corner of this slide. Okay, now let's move to the method. This picture represents a framework that I implemented for organizing a digital twin systems step by step and organizing and structuring its aims, tools, methods, resources, and actors. It stores, for example, all the information needs that we need for the digital twin implementation, the information requirements, the digital twin uses, the deliverables to produce, and so on. I know that this diagram seems very chaotic, like a sort of nebula, but the most important point you have to keep in mind for this presentation is that framework is composed of different entities, and the most important entity for this presentation are the information loops that describe the capability levels of the digital twin systems. So I identified 4 steps, 4 loops that are a descriptive loop, an analytical loop, a predictive loop, and a proactive loop. So I don't want to bore you with all the methods, that is a quite boring and long stuff, but for this presentation I tried to identify 5 main steps, main key points that I followed to to define the digital twin services with some practical application. They are ontology data modeling, topology data modeling, information templates definition, data collection infusion, and dashboard design. So first I conceptualized ontology data models that virtually represents the physical elements that we need to investigate to digitize with the digital twin systems, as well also their properties and their relationships. For example, here you can see some IFC elements that are IFC building, IFC zone, IFC spaces, but also different properties attached to these elements, different data models that store these elements, and different naming convention that I used as vocabulary for implementing this digital twin system. Then I modeled some elements of this ontology in a BIM model, and I abstracted this BIM model with a topologic model that is a lightweight model that is high interoperable with building performance simulation tools. And so in order to get data about the performance of this case study, I used the topologic model as a medium between BIM and BPS. Working with VPL, so visual programming tools, I implemented some workflow to carry out an energy analysis of the buildings, a daylight analysis, a pathfinder analysis, and so produce relevant data even if also based on simulations, about the energy consumption of the building, the comfort of users, and finally about also the safety of these buildings, in order to build up a sort of a holistic baseline model. Finally, all the data produced by BPS software were stored in a relational database and attached to the elements of the ontology that was defined in the BIM model. This allows for relating different kind of data, and allow also to summarize and visualize this data with some important KPIs that are dynamic KPIs for each phase of the building and for each hour of the year, and also to visualize this data on building spaces, such as you can see in the right part of this slide. And in the last point of this implementation, I built up some interesting dashboard to visualize this data that could be used by building administrator to know, for example, on the left, how many how many occupants are planned to be in the building every hour of the day, every hour of the year, in each space of the building. And on the right, for example, we can visualize relevant results of energy analysis, such as, for example, the predicted temperature inside each space of the buildings during each hour of the building. It is important to note that all these data are related to the number of occupants in the building, so that was inputted in the energy analysis. Going to conclusion, the next steps of my research can be identified by three different keywords that are open, on the web, and in real time. So I want to use more open data, open formats for achieving interoperability with BIM and BPS. I want to build up some web-based dashboards, maybe changing my platforms. And finally, I want to introduce some sensors inside the buildings in order to allow the real-time energy management of some significant spaces. So I ended with my presentation. I want to thank you for your attention, and please, if you have any question or if you want to write me for more details about research, I will be very happy to answer your needs. Thank you.